Hello dear friends, delighted to meet you once again. For the last JEE Mains 2025 exam, we could see almost 24 questions from ray optics alone. From the second year chapter ray optics, there appeared almost 24 questions. Now this video gives you solution for those 24 questions. 24 questions from ray optics for JEE Main 2025. Let's go to the first question. Given is a thin convex lens of refractive index mu and each side having radius of curvature r. One side is polished for complete reflection. At what distance from the lens an object be placed on the optic axis so that the image gets formed on the object itself? So this is a silvered lens. You have an equiconvex lens whose radius of curvature is capital R. It has a refractive index of some mu or n, whatever you call it. Now, one side of this lens is silvered, and such a device is called silvered lens. You know that silvered lenses will act as effectively mirrors, spherical mirrors. When you polish the surface of any lens, then certainly they will behave as convex or concave mirrors, depending upon the shape of the lens on which you are polishing. Here it is said that it is an equiconvex lens. They say that the lens is supposed to be having a radius of curvature capital R and the refractive index inside, let me for a moment say that it is some n. They say it is mu. Okay, I'm used to n. So it is n the refractive index inside. R is the radius of curvature. Now for this device, you know that this device will function as a concave mirror. When you pass some light like this, certainly after refraction, reflection and all, these light rays will come back and meet at this point. So this is the principal focus of the device. So this is ultimately acting as a concave mirror. Now what is the effective focal length of that concave mirror? Of course, you must get the equation memorized. Of course, the focal length of an equiconvex lens silvered is directly given by some expression. Yes, you must get it by heart. Actually, it is given to be equal to, focal length is given to be equal to r divided by 4n minus 2. This is some equation you must get by heart. Now, n is supposed to be the refractive index, r is the radius of curvature. So, an equiconvex silvered lens will behave as a concave mirror whose focal length is given by this expression. That is it. Now, if you want further clarification, of course, I can give you. If you want to see how you got this result, of course, it can be easily derived because, the focal length of this device can be easily calculated using the power formula. You know that the effective power of this device is given to be equal to, if it is PL the power of lens and PM the power of mirror, then the power of silvered lens is given to be equal to 2PL plus PM. This is the way we calculate the total power of this device. Now PL stands for power of lens and PM for mirror. Now what is power of lens? Power of lens is equal to 1 by F of the lens. Here L stands for lens. Now FL, focal length of lens. Remember, this is an equiconvex lens. Equiconvex lens has a focal length. You know that focal length of equiconvex lenses r by 2 into n minus 1. That is the focal length of equiconvex lens. So when it becomes power, of course, it is 1 by r by 2 into n minus 1. In other words, when you take the reciprocal, you will have 2 into n minus 1 divided by r. This is the power of the lens part. Similarly, power of the mirror part. Power of any spherical mirror is given by this formula. It is minus of 1 by Fm, where Fm is a focal length of the mirror. Now, you know that focal length of mirror is actually r by 2. If r is the radius of curvature, certainly it's r by 2. Now, that r by 2 is negative because it is a concave mirror. And that gives you some 2 by r also. Now, let's find what's the total power. Total power is 2PL plus PM. So, 2 into PL is okay, 2 into n minus 1 divided by r. That plus then comes PM, which is 2 by r. Simplifying this, you will get total power as 4n minus 2 divided by r. So that is the total power of the combination. If you have the full combination, the total power is given by this. The fact is that this device will function as a concave mirror whose power is given by this expression. That's power. Now, if you want to find what is the focal length, of course, focal length is a reciprocal of the power. That is r by 4n minus 2. Okay, so that's the story of that equation. Anyway, you must get it by heart. That is what I advise. So this is the equation for focal length. Now let's come to the question. They ask you, At what distance from the mirror, from the lens, an object must be placed on the optic axis so that the image is coinciding with the object itself. Usually in the case of a concave mirror, it happens, sometimes at least. When you keep an object exactly at some point, image also will be formed at the same point, and you know where it must be kept. If you're keeping the object exactly at 2f of a mirror, a concave mirror, then the image is also produced at the same 2f. So you have to keep the object at a distance 2f. If you keep an object here at a distance equal to 2f, image will be coinciding with the object. So the final answer, they ask you what's the distance at which the object must be placed. Your answer is, it is u equal to 2f. So this is equal to 2 into, now f is r by 4n minus 2. Simplifying this, you'll have r by some 2 into n minus 1, okay, because this 2 can be taken as common. It becomes r by 2 into n minus 1. So r by 2 into n minus 1 is the distance at which you must keep it. Actually, this is the answer. Now, this mu is what I meant as n here. N is a refractive index of the medium that is used to construct the glass. Okay, that was question number 1. Let me go to the next question. In the diagram given below, there are 3 lenses formed. Considering negligible thickness of each of them as compared to radius R1 and R2, the radius of curvature of upper and lower surfaces of the glass lens are given to be R1 and R2. Then what is the power of the combination? So here you can see, forget about the container, you can see actually a combination of 3 lenses here. One is a glass lens, and you'll see that there are other 2 liquid lenses also. I'll just show the parts. First of all, this will act as a plano-convex liquid lens. So that's a convex lens. That's a liquid lens. And the refractive index of that medium is given to be 4 by 3. Now the radius of curvature of that part is given to be R1 here. Now comes another medium, which is glass. So this is glass. Okay, I'm showing here this as a glass lens. It's a concavo-convex glass lens. The 2 sides are curved actually. It will also behave as a converging lens. Anyway, that is concavo-convex lens made of glass. And finally, you'll see some portion here also. That also will function as a lens. So this is the 3rd lens. That's a plano-concave liquid lens. So there are 3 lenses in the figure. You are required to find the total power of the full combination. So to find the total power, what we do is this, we will find their individual powers in air. Each and every lens will be considered to be separate lens. They will have their own powers in air. If you get their own powers in air, just add all these powers to get the total power of the system in air. That is what we do. So for that, for convenience, I have divided this diagram into 3 lenses for your convenience. Okay, I begin with, first of all, this one. See the shaded portion. I have, sorry. I'll take this one first. Okay, let us go in order. This one is a plano-concave lens. You know which lens is that? In the original figure, it is this. I begin with this. Let's say that this is the device. So that's the first lens I consider. It is plano-concave lens. And in the whole discussion, we are assuming light to be passing in one way. Let's say for convenience, it doesn't matter whether light is passing from left to right or right to left. That doesn't affect the result at all. We just need a reference ray to obey the rules of sign conventions and all. That is why I took light ray in this way. Now this is the way light ray is supposed to pass. Now refractive index of this medium is said to be, how much is that? Yes, it is 4 by 3. This is 4 by 3. And the radii of curvatures are shown as in the figure, R1, R2. You see that this is the way R1 and R2 are given. So this is R1, this is R2. In the same way, I have followed R1 and R2 in this figure also. Okay, let me begin with the power of the first combination for a first lens. Let me say the power of this lens is some P1. I'm writing the expression for P1 using lens maker's formula. I hope you remember lens maker's formula. According to lens maker's formula, power is given by N2 minus N1 divided by N1. That's a full expression. That into 1 by first radius minus 1 by second radius. Forget about the names. R1, R2 in the expression stands for first radius and second radius. Remember. Now the first lens I consider, P1. Power of the first lens P1 is equal to N2 minus N1. N2 is 4 by 3 minus N1. I remind you that every lens is supposed to be surrounded by air. So you have to find the focal length of each lens in air or power of each lens in air. Then you add all the powers to get the total power of the combination in air. So every lens is supposed to be surrounded by air. Remember that. So in that way, 4 by 3 minus 1 divided by 1, that into 1 by R1, 1 by first radius. See, for the first lens, this is the first radius. Light hits here first. So that radius is actually infinity. That is what I use here, 1 by infinity minus. Now the second radius comes and the second radius is this. This is what we called actually R2. Okay, so that's R2. It is 1 by R2 then. That is the power of the first lens. 4 by 3 minus 1 is 1 by 3. So this is going to give you 1 by 3 and 1 by infinity is 0. I have R2. Yes, it is negative because it is a concave lens. Yes, that is power P1. Let's go to the power P2. Now remember, this lens, second lens, okay, I'm calling it a concave or convex lens. The power is given to be P2. Okay, again, the surrounding medium of that lens is also supposed to be air, right? Remember, the refractive index of this lens is 3 by 2. So that is N2 minus N1, that gives you 3 by 2 minus 1 divided by 1 again, that into 1 by R1 minus 1 by R2. 1 by R1 means first radius. See, light is hitting this surface first. So this radius is first radius. In my figure, it is R2. So that first radius is R2 here, which is plus R2 minus second radius is this. So finally, light, see, first after hitting the surface, then light hits here. That is second surface whose radius is supposed to be R1 as per the given data. So that is 1 by R1. This is it. Now this is power of the second lens. Now 1 by 2 is 3 by 2 minus 1. So it gives you 1 by 2 into 1 by R2 minus 1 by R1. That is the power of second part. Let me make it simple. It is 1 by 2 R2 minus 1 by 2 R1. That's the power of the second lens. That is, remember, P2. Okay, we come to P3 now. Now the final lens we consider is this. Okay, that lens is also made of water surrounded by, again, air. Remember, its surrounding medium is also supposed to be air. Now it's a planar convex lens. Again, we'll apply your lens maker's formula. It is P3 now. P3 equal to N2 minus N1. N2 is 4 by 3 minus 1 divided by 1. That into 1 by R1, 1 by first radius. The first radius is, when light is coming in this way, you know, this is the first radius. That first radius is supposed to be R1 as per the given question. So 1 by plus R1 minus second radius is this. Look at this. This is the second radius. Light hits here, then here. So this is the second radius. That second radius is plane. Therefore, the radius of curvature is infinity. Okay, so that's infinity. This gives you how much? 4 by 3 minus 1 is 1 by 3. 1 by 3 into R1. I have 1 by 3 R1 as P3. So these are the individual powers. Now please take a look at the powers. P1 is this, P2 is this, and this is P3. Now we add all the powers to get the final power. Okay, to have the final power, it's just a matter of adding all the powers. P1 plus P2 plus P3, nothing else. It's only a matter of adding powers. It is minus of 1 by 3 R2, that's the first power, P1 plus P2. What is that? P2 is given to be this. This is P2. 1 by 2 R2, 1 by 2 R2 minus 1 by 2 R1. That's the power of the second lens. Now the final power is, okay, P3, which is 1 by 3 R1. So these are the powers to be added. Okay, let's see what happens when these two are added. 1 by 2 minus 1 by 3. 1 by 2 minus 1 by 3. 1 by 2 plus 1 by 3. 1 by 2 minus 1 by 3 is what? It is 3 minus 1. Okay, it is 1 by 6. This is equal to 1 by 6 R2. Okay, which is plus. Now I have some minus of 1 by 2 plus 1 by 3 minus 1 by 2 is going to be minus. Okay, it is 1 by minus of 6 R1 also. So that is it. Okay, finalizing. Yes, this is equal to, finally, 1 by 6 can be taken common. That into 1 by R1 minus 1 by R2 minus 1 by R1. That is my answer. Let us confirm that. Yes, you can go with this because my answer has 1 by 6 into 1 by R2 minus 1 by R1. But in the answer, they have reversed it. Okay, no issues. I can just add a negative sign and reverse this. Minus of 1 by 6 into 1 by R1 minus 1 by R2. That is also equally correct. So this is the power, total power of the given combination. That's how the option becomes 4. Okay, that was question number 2. Let's go to the next question, which can be slightly difficult. The driver sitting inside a parked car. Inside a parked car is watching vehicles approaching from behind with the help of a side view mirror, which is a convex mirror with a radius of curvature r equal to 2 meter. Another car approaches from behind with the uniform speed of 90 km per hour. Okay, you'll have to change that into meter per second to get the answer in SI units. Okay. When the car is at distance 24 meter from him, what is the magnitude of acceleration of the image of the car in the side view mirror? That is what they ask. They say that it is A. Then they ask you, what is the value of 100A? What is the numerical value of 100A is the question. So the whole question is about acceleration of image. And here, conveniently, the most comfortable part of this question is that the mirror is stationary at least. Only the object behind the mirror is moving. Object behind the mirror is another vehicle. And when the vehicle is moving behind a car, a stationary car, you can see the image of that car also moving inside the mirror. Now, the whole question is about how fast the image is moving, not how fast. They are just asking you what is the acceleration of the image of the car. Okay, let's begin with, first of all, velocity. This is the convex mirror. If you have an object, okay, forget about car and all. Let's say this is the object, this is O. Now, correspondingly, there will be a virtual image, because it's a convex mirror. Anyway, it's an image I. Now, the distance to object is supposed to be U and distance to image is supposed to be V. And the focal length of the mirror is supposed to be F. Whatever be the nature of mirror, be it convex or concave, you know that the focal length, object distance and the image distance is given by certain expression. They are related by certain expression. 1 by V plus 1 by U is equal to 1 by F. That is actually the equation connecting the distances. This is the distance formula for any mirror. Now, this question is about velocity and finally acceleration. Without finding velocity, we can't find acceleration. To find velocity, we differentiate all the terms with respect to time. So, we are differentiating every term. First of all, 1 by V is differentiated. When you have 1 by V differentiated, you'll have 1 by V squared, minus of 1 by V squared, that into dV divided by dt. Remember, dV by dt stands for the velocity of image. Now, plus 1 by U squared minus of again, that into du by dt. Yes, that is equal to, F is a constant here. So, when you differentiate dF by dt, you'll get 0. This tells you the equation for velocity, at least dV by dt is equal to, it is going to be minus of V squared divided by U squared, that into du divided by dt. Now, what is this dV by dt and du by dt? You know that it is this du by dt which is going to be the velocity of object, because this is u. So, the rate at which this u is changing is actually called the velocity of object. So, let me use VO for that. So, this will be written as VO. Similarly, dV by dt is the rate at which this distance is changing. So, the rate at which that distance is changing is called the velocity of image VI also. So, I will be using VI to represent this. VI stands for velocity of image. So, here comes at least the velocity expressions. Velocity of image is equal to minus of. Now, V squared by U squared, for a mirror is linear magnification square, because you know that M for any mirror is minus of V by U. So, when you take M squared, certainly we get a V squared divided by U squared. So, this V squared by U squared is written as M squared, that into velocity of object. So, this is the equation for velocity. But remember, this question is about acceleration. So, you must be careful now. We must differentiate it once again to get acceleration. So, acceleration of image AI is equal to, when you differentiate both sides, you'll get acceleration. That's what I'm trying to do. Okay. So, let me write dV by dt on both sides. D by dt, I'll take d by dt on both sides now. Yes, d by dt of VI, velocity of image, is equal to, yes, it is d by dt of minus of M squared times VO. Okay, that's it. Now, remember, M here is a variable, because as the object is moving, the distance, because magnification M is given to be, the best way I can describe magnification for a mirror is F by F minus U. And as the object is moving, U is changing, so M is a variable here. But VO is not a variable because they say that velocity of the object is a constant value, because they say that it is moving with a uniform speed of 90 km per hour. So the velocity of object VO is a constant. You can just take it as a constant here. In that way, you can easily differentiate this. VO is actually a constant, so just keep it as VO. Now it is only a matter of d by dt of m squared minus of course there is a minus sign, I am not leaving it. It is minus of that. Now d by dt of 2m, d by dt of m squared, d by dt of m squared is okay 2m. And m is a variable, therefore it is dm by dt also. Simplify this, you will get the equation for acceleration, because d by dt of vi is actually acceleration. Now let's see what is this dm by dt. What is this dm by dt you will get when you differentiate this. So let's do that. Dm by dt here, when I differentiate, I'll get f is a constant, f minus u is a function, so that's going to be f by f minus u the whole squared. Now u is the variable, therefore it is du by dt also. Yes, there is an extra minus n because it is minus u. Okay. Now this is equal to f by f minus u whole squared can be written as, okay, I'll do one thing, f by f minus u. To make it simple, I'll multiply f here. Okay, just wait. I'll multiply f here. Okay, let me confirm what I'm doing. I'll multiply f here and later f here. Why? Because I get here then f by f minus u whole squared. F by f minus u whole squared is going to be f m squared also. So that's what I'm doing. Okay, so I have some adjusting. I can say it is f squared divided by f minus u the whole squared. There is another f appearing here, that into du divided by dt. Now this can be written as, of course, it is m squared divided by some f into du divided by dt. And remember, this du by dt is again the velocity of the object. There is a minus sign also. Did I miss anything? F by f minus u whole squared. Yes, du by dt. This is it. Now finally, let me substitute. Acceleration of image AI is equal to minus of VO, that into 2m into dm by dt. What I got is some m squared divided by f, that into VO. Of course, we have a minus sign. Forget about signs here finally, because that will just tell you what the direction is. I am writing finally the magnitude only. Okay, finally, here comes the equation for the acceleration. Acceleration AI is equal to, yes, it is 2 times m cubed VO squared. VO stands for the velocity of object, divided by f. My dear friends, I will ask you to get this equation by heart. Best way is to get this by heart. Acceleration is given by this expression. The magnitude of acceleration at this is given by this expression. Okay, now let's start putting values. I'll use this equation here. Okay, AI is equal to 2 times m cubed V0 squared, VO squared divided by f. That's the equation for acceleration. Let's come to now values. What is magnification here? Let us calculate magnification first of all. Magnification for any mirror is given to be f by f minus u. And here f is, come to the focal length of mirror. It is said that radius of curvature of the mirror is 2 meter. If radius of curvature of mirror is 2 meter, then the focal length of the mirror is 1 meter. So 1 meter is focal length. I'll put that value. And it's a convex mirror also, it is plus 1 then. Okay, again plus 1 minus. What is u here? Said that the object is at a distance of how much? 24 meter. This is the distance. That is the distance u. And that 24 is backward. Remember, if you have an object here, this is 24, but that 24 is measured opposite to the direction of velocity, direction of light. So that f must be, u must be considered as minus of 24. So m here, the linear magnification produced by the mirror, at least at this moment, is 1 by 25. So that is m. Let me give values now. 2 into, it is m cubed. M cubed is 1 by 25 cubed, that into. Now what is VO? Velocity of object. It is given to be 90 km per hour. So 90 km per hour is 90 into 5 by 18, that much meter per second. This is going to be 25 meter per second. Okay. So VO in meter per second is 25 meter per second. So that is 25 whole squared because it is V squared now. Divided by focal length, it is 1. Finally, this is 2 by 25. 25 squared is cancelled. It is 2 by 25. This is acceleration of the image actually. This much meter per second squared is acceleration. Okay, I have written only the magnitude here. Now let's come to the question. They ask you, what is the value of 100A? 100A. So you have to multiply that with 100 and finally put the numerical value of the question answer. So 2 by 25, that into some 100 is there. So finally the value is going to be 8. So the numerical value of the answer is 8. Answer is 8 meter per second squared. 100A, if it is 100A, that is 8 meter per second squared. That is question number 3. So I'll advise you this. If you can, I would ask you to get this equation by heart. Acceleration of image in the case of spherical mirror, that's given by this standard equation, which will be helpful in many other questions as well. Okay, now let's move on to the next question. That's going to be the 4th question in my paper. I think I missed a negative sign here, didn't I? Yeah, of course. Because m is equal to f by f minus u. Look at this part. I think I missed a negative sign because m is equal to f by f minus u. Then the dm by dt will be equal to minus of f by f minus u whole squared. That into again a du by dt is negative because u is negative. So it will be actually plus m squared f by vu. So in that way, the final answer will have a negative value and all. Okay, but don't take it seriously because the final answer is only about the magnitude, numerical value of that 100A. So it's only 8, doesn't matter. Actually, it has a negative sign here, but at least that is not serious in that question. Okay, here is question number 4. A symmetric thin biconvex lens is cut into 4 equal parts by 2 planes AB and CD as shown in the figure. If the power of the original lens is 4 diopter, then the power of the part of divided lenses. Easy question. You know what happens when you split a lens. When you cut lenses in various ways, you must know what happens to focal lengths. If it is focal length, I will begin in this way. For example, if f is a focal length of the first lens, and suppose it is cut along this way, I am cutting this lens in this way. And if you cut a lens, equiconvex lens in that way, you will get 2 planar convex lenses and 1 planar convex lens is shown here. If f is a focal length of the original lens, then you must know that the focal length of that planar convex lens will become 2af. That's the way the focal length changes when you cut the lens in this way. But now, if you are cutting the same lens in this way, nothing will happen to focal length. It will continue to be the same 2af. This is the story of focal length. Let's talk about power. If it is power, let me begin with power now. If P is the power of the original lens, certainly the power of half the lens will be P by 2. Now, even if you cut that lens in this way, nothing will happen to power. It will become P by 2. Simply, that's the logic. Okay. Now, they say that it is 4 diopter the power of the original lens. That will become 2 diopter after cutting it. And that will continue to be 2 diopter even if you cut it again like this. So, the answer is 2 diopter. That's option 3. Okay, question number 5. Actually, in my paper, this question appeared. Actually, it is from wave optics only, but still we answer it here. It is a misplaced question, at least for this chapter, but still I am ready to answer that. Transparent film of refractive index 2 is coated on a glass slab of refractive index 1.45. What is the minimum thickness of the transparent film to be coated for maximum transmission of green light of wavelength 550 nanometer? Assume that light is incident nearly perpendicular to the glass surface. It is about transmission actually. It is not about partially reflected light. It is transmitting light. So here what they say is this, let me roughly show it. There could be some glass plate like this which is very thick, and maybe there's a small coating that is given on the glass plate. So this is that coating. So this coating, is having a refractive index of n is equal to 2 as per the question. And the glass slab, so-called glass slab, is having n is equal to, it is 1.5 also. 1.4, not 1.5, it is 1.45. That is the refractive index of the glass slab. Okay, now surrounding medium here is air and this is air. That's how the experiment is explained. So there is a coating. That coating, once again I'll highlight, this is that coating. Okay, now what you see here is glass. This is actually glass. Now, what you are required to find out is this. There is light actually falling on this surface, which will penetrate through the film, and further, it will be transmitting through the glass slab. So, the whole question is about what is the condition or thickness of the film so that maximum transmission will take place, or the transmitted light is having maximum intensity. In other words, the transmitted light must be having mutual constructive interference. So this is about interference in thin films. So let me just give you a better figure. This can be considered that coating. Okay, this is the red you can see here is a coating. Okay, so this is the coating that is mentioned in the question, and this is supposed to be glass. So that's the way I consider the figure. So the n of this part is given to be 2. This is air, so n is equal to 1. And here it is n is equal to 1.45 or so, isn't it? It's 1.45. Yes, it is glass. All right. Now let's see what happens to light here. What I'm trying to show is this. Maybe this is the way light is falling almost normally on the film, and 90% of light will actually transmit because everything is transparent. Further a transparent surface again. Therefore, light will finally pass like this. That's the way we expect light to pass. But on the way, light will be having some partial reflections. Let me show or highlight what is happening in partial reflection level. Maybe this is the way light comes, it transmits, it hits the second surface, and a small part will be actually transmitted, while a major part will be transmitted like this. A small part will be reflected like this. Now that reflected part will again come back after partial reflection, and that will again pass like this. So we have two waves here to consider. This is 1 and this is 2. These two waves can actually interfere. Now this is the transmitted light. Remember, this is actually what they call the transmitted light here. Now this transmitted light must be giving you maximum intensity. So for that transmitted light to give you maximum intensity, they must involve in constructive interference. In other words, the path difference of these two waves, must be equal to some n lambda for constructive interference to take place. So the question is, what's the condition for that? Okay, that's it. So let me come to now the way reflection is taking place. Let me depend on certain lines here. It's very difficult for me to draw waves here. Okay, this is the incident light. It transmits. A major part of this light is going like this. 90% of light will transmit because it's a transparent film. Okay, now a small kind of reflection is expected here. This is a partial reflection. After partial reflection from second surface, light is further partially reflected from the upper surface also. So this is the way it comes back. Now this is the way it finally goes. Now this is 1 and this is 2. Now what is the path difference here? You know that this wave 1, it is actually passing directly like this. But wave number 2 actually traveled an additional distance as I have shown here. So that additional distance is going to be the path difference here. Now what is that additional distance? It is said that this thickness is supposed to be some t. So it's said that thickness of the small film is in fact some, question is to find what is the thickness of that film. Okay, we'll come to that. Let me assume that t is the thickness of that film here. And the refractive index n for that film is given to be 2. Anyway, it's supposed to be mu. Okay, let me call it mu. Now, see, as it is normal incidence, this length is equal to t. This length is another t. But remember, so there is an additional 2t here. But 2t is inside the inside the film coating. When a distance of 2t is considered inside a medium, then you must always consider optical path. If mu is the refractive index of that film, then remember 2 mu t must be considered as the optical path. 2t is actually the real path, geometrical path, but you have to multiply that with mu to obtain the optical path. So the extra optical path the light wave have covered is 2 mu t, and that is the only path difference here. So wave number 1 and wave number 2 will have a clear path difference of del is equal to 2 mu t. That is the equation for the path difference, where mu is the refractive index of this film, or you can call it n. So, okay, that is refractive index. Now, usually there is another possibility of a phase difference. Whenever light is undergoing a reflection at denser surface, a phase difference of 180 is expected. But when light is undergoing a reflection at a rarer surface, there is no phase difference at all. And here, look at the reflection. The first reflection, it is here. Now here, reflection is taking place when light is passing from n equal to 2 to n equal to 1.45. In other words, the reflection is taking place at rarer surface. So there is no phase difference there. Now look at what happens here. There also reflection is taking place. This is the way light is reflected. There also there is no phase difference because light was passing from n equal to 2 to n equal to 1. Again, the reflection is taking place at a rarer surface. So there is no question of any additional phase difference here. The only path difference is 2 mu t and there is no additional phase difference. So the path difference is 2 mu t. Now they ask you what's the condition for maximum or constructive interference. So let's come to the condition for constructive interference now. Constructive interference takes place when del is equal to some n lambda. And that del, the path difference here is 2 mu t. So 2 mu t is equal to n lambda is the condition for constructive interference. They ask us what's the thickness of the film for this. So t is equal to n lambda divided by 2 mu. Your answer is this. Actually, it's a series of answers, but they ask you what is the minimum thickness. You will have a number of thicknesses for this to happen, but they ask you what is the minimum thickness. If you are required to find minimum thickness, then give the value for n as 1. If you want to find the next thickness, n is equal to 2, the next thickness, n is equal to 3, and so on. And here, this is minimum thickness, so you must give n as 1. So finally, this is my answer. It is 1 lambda divided by some 2 mu. That is it. So the minimum thickness t is given by lambda by 2 mu in this question. Now coming back to the data, thickness t is lambda divided by 2 mu. Now what is lambda? It is given to be 550 nanometer. Okay, I'm not changing unit. I'll answer it in nanometer. Divide by 2 mu, 2 into. Now what is mu? Mu is given to be 2 here. The refractive index of the coating or the film is mu here. So that mu must be considered as 2. Remember, in the expression 2 mu t, remember this one, don't get confused. This mu is actually the refractive index of the coating or the thin film. Yes, it is 2 into 2. What is that then? 550 divided by 4, isn't it? 550 divided by 4 nanometer is your answer. This looks like it is some 137.5 nanometer. So that is the minimum thickness for which this will take place. So for the best transmission, for the transmitted light to be interfered constructively, the condition is that thickness must be minimum 137.5. Yes, your option is 1. Let's move on to the next question. A spherical surface of radius of curvature r separates air from glass with a refractive index of 1.5. The center of curvature is in glass medium. A point object O is placed on the optic axis of the surface so that a real image is formed at I inside glass. The line OI intersects the spherical surface P and PO is given to be equal to PI. Then the distance PO is equal to. So we have a spherical surface, an object is placed in front of it. It will produce an image of the object. Now, ultimately, they said that distance to object and distance to image are equal from surface. That is what they meant by saying that PO is equal to PI. Let me show a diagram here. This is the spherical surface. It is said that n is equal to 1.5 for glass. And on this side, I can say it is air. So, n is 1. Now, here is a point object. What they say is that this point object will send light in this way and that will produce an image on the other side. So, this is the object, this is the image. Now, it is given that the distance OI, let me say object is OI is the image. So, that line joining is cutting the surface at a point P in such a way that this distance OP and this distance IP are equal. In other words, let me make it simple. If this is x, then the other is also x. Simple as that. They ask you what is the value of x now. So this is only a distance question. Object, image, radius of curvature, the distances, etc. are given by certain expression for spherical surface. I hope you remember. It is n2 by v minus n1 divided by u is equal to n2 minus n1 divided by radius of curvature r. That's the way distances are related in the case of a spherical surface. Now here n1 stands for the first medium, n2 for the second medium. R, U, V, you all know. So let's put values now. N2 is okay here, 1.5. This is the N2 because it is second medium. That N2 is given to be 1.5 divided by V is the distance to image. And we have supposed that that distance V is equal to X. So that is plus x also. I would say plus x minus. Now comes n1. n1 is okay, first medium, that is going to be 1. So n1 is 1 by u is the distance to object. So this distance is actually u, and that's a measurement taken backwards. So u must be given actually a minus sign. U equal to minus of x. You know the rules of sign. So this is equal to n2 minus n1. Yes, 1.5 minus 1 divided by radius is okay, capital R, and that R is to be determined. Okay, let's simplify. Simplifying this, I have 1.5 plus 1 divided by x here is equal to 0.5 divided by r. Because 1.5 plus 1 is going to be 2.5 divided by x is equal to 0.5 divided by r. Yes, you will simplify this to get what? Yes, x is equal to 5r. So the distance x is equal to 5r. If this is 5r, this is also 5r. That is the result. They ask you what's the distance to the object. In other words, they are asking you what is the distance OP, and the answer is 5r. Okay. Yes, you go with option 1. That was question number 6 in my paper. Okay, 7. Given a thin convex lens of a refractive index mu2 kept in a liquid of a refractive index mu1 in such a way that mu1 is less than mu2, having radius of curvatures r1 and r2. The second surface that means R2, a surface with radius of curvature R2 is polished, silvered. Where should an object be placed on the optic axis so that real and inverted image is formed at the same place? So this is a silver lens again. Silver lens immersed inside a liquid, and you have kept an object somewhere near the silver lens in such a way that the image is coinciding with the object. So where should you keep it? That's a question. You know that every silvered lens will function as a spherical mirror. Now, when it is equiconvex lens silvered or biconvex lens silvered like this, it will behave as a concave mirror also. So, in fact, the device is finally going to behave like a concave mirror. So, this is going to be the optical equivalence of the system. It will finally behave like this. This is the concave mirror which is equivalent to the given system. Now, let's find what is the focal length of that concave mirror. Now, you know that it is a silver lens. Equivalent focal length is given by power first of all. The best way to calculate the focal length is power. I told you that the total power of any silver lens is generally written as 2PL plus PM, where PL is the power of the lens in the given medium and power of mirror is PM also. Let's come to PL first. PL, power of lens. It is given by lens maker's formula. It is N2 minus N1 divided by N1. Okay, you know the equations there. So I can say it is mu2 minus mu1 divided by mu1. Remember, in the question it is said that this is mu2 and the surrounding medium of the lens is mu1. That into 1 by r1, 1 by the radius. Okay, this is the way we are expecting light to come, and the first radius is r1, second radius is r2. So 1 by plus r1 is the first radius minus 1 by r2. Remember, r2 is a negative radius because this is the second radius. You have to measure r2 in this way. So that is negative as per the sign convention. So this is the power of the lens part. Okay, this is equal to mu2 minus mu1 divided by mu1 again, that into, okay, 1 by r1 plus 1 by r2 gives you r1 plus r2 divided by some r1 r2. This is at least PL, I would say. Okay, let me simplify it. It is mu2 minus mu1, that into r1 plus r2, because the answer must come in this way, no? Divided by mu1 into r1 r2. That is what we have now. This is PL. Okay, that's power PL. Finally, we have to take the twice of this value and add it to PM. Okay, let's wait. That is PL only. Let's come to power of the mirror part. Now, mirror part is this. Look at this. This is the mirror part. The radius of curvature of the mirror part is R2. And power of mirror, you know, generally is given by minus of 1 by FM, where FM is the focal length of mirror. And here, the radius of curvature of the so-called mirror is R2. So, the focal length must be R2 by 2. So, this is minus of FM, which is going to be R2 by 2. But remember, it's a concave mirror. The radius of curvature is negative. So, minus of R2 by 2. It gives you some 2 divided by R2. That's the power of the mirror part. Now we come to the total power. Total power is equal to 2PL plus PM. Okay, PL is this. Okay, 2PL, 2 into. Okay, that's 2. I think there is another 2 here. Here there is a 2. I'm going to take another 2 here. So I can take that 2 common. Okay, let me say one step at least. 2 into. It is PL, which is going to be mu2 minus mu1, that into R1 plus R2. Yes, that divided by mu1 into R1 R2. That plus 2 by R2. I am taking 2 common. Okay, so I can say it is only 1 by R2. I have taken 2 common. So this is 1 by R2. This is the total power. Okay, to make it simple, I can take R2 also common because there is an R2 here, here is an R2. Okay, let me simplify it as 2 divided by R2 then, that into, let me expand the brackets on the top. It is mu2 R1 plus mu2 R2, okay, minus mu1 R1 minus mu1 R2 when I expand it. Now I am adding it because the 2 by R2 is taken common. So I have, yes, this is gone. I'll just make this R2. It is gone to here. Okay, R2. So plus 1. All right. This is equal to then plus mu1 R1. Right. Divided by, finally, it is mu1 R1. This is the power of the total power of the system. I think there are certain terms to cancel. Which one are they? Plus mu R1 minus mu R1. There's only mu2 into, okay, mu2 into R1 plus R2. Yes, this is equal to 2 by R2. That into mu2 into R1 plus R2. Yeah, minus what? Mu1 R2. Yes, that is mu1 R2 divided by mu1 into R1. That is the power of the device. Now we come to focal length, because ultimately what we want is the focal length of the device. To get focal length, we can take twice of this value. Okay, let me take this part. All right. Now coming to power. Sorry, focal length. Focal length F is equal to 1 by P. So the focal length of the effective combination is mu1 R1 R2. Okay, mu1 into R1 into R2 divided by 2 into mu2 into R1 plus R2. Yes, minus mu1 R2. Anything missing? No. This is the focal length of the given system. Now they ask you where you should keep the object in such a way that image is formed exactly at the position of the object. So if you are keeping an object somewhere here in front of a concave mirror, certainly image is also produced at that same point when the distance u is equal to 2f of the device. So ultimately your answer is 2f, because you have to find the position of the object in such a way that image coincides with the object. So finally the u is going to be 2f. So when you multiply the whole thing with 2f, of course this 2 is cancelled then. So let me come to the final answer. It is mu1 R1 R2 divided by mu2 into R1 plus R2. That minus mu1 R2. That is our answer. Mu1 R1 R2 by mu2 into R1 plus R2. Yes, this is it. We got it. It is option 1. That was question number 7. So that was slightly lengthy because it's a silver lens. Not only silver lens, it is a biconvex silver lens. Had this been equiconvex silver lens, it would have been much more easy. Okay. What is the shift, lateral shift of a ray refracted through parallel sided glass slab of thickness h in terms of angle of incidence I and angle of refraction R? The glass slab is placed in air medium. I think you must get it by heart. See, basically, the question is about this. This is a glass slab. You can assume that this is glass slab. I think you can see it in your monitor. This is the glass slab. Now, here it is supposed to be air. This is also air. Now, when light is passing through a glass slab, it takes bend. It bends twice actually, because when passing from air to glass, it bends. Now, again from glass to air, it again bends. So, actual path of light ray, had this been the actual light ray, it would have actually passed in this way. Sorry. Yes, this is the way we expected light to pass. This is the actual path of light ray. Did I make a mistake? No. So this is the actual path. If that is the actual path of light ray, it takes bend twice and passes like this. So this is the emergent ray. Now what is a lateral shift? Lateral shift is supposed to be this. What is this gap? Is actually called the lateral shift. Now the thickness of the slab, okay, this thickness, you know, that is supposed to be some t. I'll give you an expression here. There is no time for derivation and all, you know, we are just answering a question. Now I'm also supposing that the angle of incidence is, okay, this is the angle of incidence. We suppose that this angle of incidence is I and the angle of refraction is R. Refractive index of this is N also. Okay. Now the equation for lateral shift is given by a certain expression. The expression is given to be x. If I'm calling it x, you know, then that is given to be equal to some t into, okay, they are using actually h for that time. See, remember, it is h they have used, but I am using t for that. Okay, t into, the equation is this. You must get this by heart. It is t into sine I minus r divided by cos r. That is the equation for lateral shift when light passes through a glass slab. This can be derived, but the derivation requires, you know, a lot of steps. So remember, that is the expression for that. Okay, so t into sine I minus r by cos r, which is h into sine I minus r by cos r, because t is equal to h in the question. So you go with option 2. That was a direct question. Concave mirror of focal length f in air is dipped in liquid of refractive index mu. Its focal length in the liquid will be. See, this is a mirror. If you immerse a mirror inside water, nothing will happen to focal length because it is reflection only. A mirror is working on the principle of reflection. It's not a lens. If you immerse a convex lens or concave lens inside water, certainly focal length will alter. But in the case of mirror, we don't find any difference at all. If the mirror performs this way in air, it performs the same way in liquid also. So introducing a liquid into the environment of a mirror doesn't change its property at all. As long as the radius of curvature of the mirror remains intact, the focal length also remains the same. So focal length is not affected. Your answer continues to be F. Even if it is immersed in liquid, it doesn't make any difference. Okay. Refractive index of the material of glass prism is √3. Angle of minimum deviation is equal to angle of the prism. Then what is the angle of prism? This is again a direct question, connecting angle of prism, refractive index, then of course angle of minimum deviation. There is a standard equation that everyone must remember. It is given by n is equal to sine a plus d by 2 divided by sine a by 2. That's a standard equation connecting angle of prism, minimum deviation, and refractive index. So this is it. Now here they say that the angle of minimum deviation, angle of minimum deviation of the prism is equal to the angle of prism. So this A and D are equal. That is what they say. And they ask you what is the angle of prism. So this D can be written as A. Okay, so I can rewrite the equation as n is equal to sine A plus A by 2. A plus A by 2 is 2A by 2. That reduces to sine A divided by sine A by 2. Okay, let's simplify this. This n is going to be, okay, sine A can be simplified as 2 sine A by 2 cos A by 2. So this can be written as 2 sine of A by 2 into cos A by 2 for the purpose of simplifying it, divided by sine A by 2. And in the process, I have the sine A by 2, sine A by 2 cancelled. So it is 2 cos A by 2. So the answer is here. Okay, let us put values. N is given to be √3. That is what they have given as a data in the question. It is equal to 2 cos A by 2. So 2 cos A by 2 is √3 means, of course, cos of A by 2 is equal to √3 divided by 2. If cos of A by 2 is √3 by 2, then certainly A by 2 will be equal to 30 degree because cos 30 is √3 by 2. Yes, therefore A is equal to 60 degree. That was it. That is question number 10. Yes, it is 60 degree. Let's move on to the next one. Easy question. What is the relative decrease in focal length of a lens for an increase in optical power by 0.1 diopter from 2.5 diopter? Power of a lens is changed. Certainly focal length also will change. So if you give a fractional change of power, certainly a fractional change of focal length is also expected. They ask you what's a fractional change in focal length. Okay, let's apply some calculus. You know that power of any lens is equal to 1 by f. To find the relative change in powers and all, let's differentiate both sides. So I'll say when I take differential on both sides, I'll get dp as minus of 1 by f squared into df. I have differentiated both terms. Now to find the fractional changes, let's divide equation number 1 and 2. Okay, these are equations. Now let me do 2 by 1. When I take 2 by 1, I have dp by p, the fractional change in power. When I take 2 by 1 is equal to, yes, it is df divided by f squared divided by f. Okay, it becomes f then, minus is there. So this is equal to df by f. So we get dp divided by p as df divided by f. Of course, a negative sign is there. Okay. The question is, what is df by f? So it is nothing but dp by p. Now what is dp here? dp is said to be 0.1. 0.1 diopter is a change in power. So that dp is 0.1 divided by original power was 2.5 diopter also. So it is 2.5. So is dp is 0.1 and this power is 2.5. All right, it's over. It's just 0.1 by 25, 2.5, or I would say 1 by 25, which is equal to 0.04. That is a fractional change in focal length. Because power is equal to reciprocal of focal length. Okay. A thin plano convex lens made of glass and refractive index 1.5 is immersed in a liquid of refractive index 1.2. When the plane side of the lens is coated for complete reflection, the lens is immersed in the liquid behaves like a concave mirror of focal length of 0.2 meter. Then the radius of curvature of the lens will be. So this is a plano convex lens immersed inside liquid and the plane surface of the lens is silvered also. Let's see what happens. Here is a lens that is immersed in water or some liquid. They say that refractive index of the lens is given to be 1.5 and the n of the surrounding is given to be 1.2. Is that correct? It's 1.2. Now this device is having a focal length of 0.2 meter. You know that this device also will behave like a concave mirror. If you take the equivalence of this device, you will see that this will be perfectly behaving again like a concave mirror. And that concave mirror will have a focal length f. You can find the focal length of silver lens using the power formula and all. As I told you earlier, the total power of any silver lens is 2pl plus pm, where pl stands for the power of the lens and pm that for the mirror. Now power of lens, pl, let me come to that. It is equal to 1 by fl, and 1 by fl for any lens is given by lens maker's formula, immersed in liquid. So that is n2 minus n1. Okay, let me write the equation for you first. n2 minus n1 by n1 into 1 by first radius minus 1 by second radius. That's the way we find the power of lens. Equal to n2 is equal to 1.5 here minus it is 1.2 then because surrounding is 1.2, again 1.2, that into 1 by first radius is okay r, whose value is not known to us now. Actually, we have to determine what is r. Minus 1 by r2. The second surface, look at it, is plane surface. When it is plane surface, certainly the radius is infinity. Okay. That is power of the lens part. 1.5 minus 1.2 is 0.3 divided by 1.2 into 1 by r. It looks like 0.3 by 1.2 is, yes, it is 1 by 4r. That is the power of lens part. Therefore, power of the power of lens part is 1 by 4r. You have to put this value of PL in the above expression. Let's come to PM before that. Now PM. PM, power of mirror. You know that the second part of the system is plane. It's a plane mirror. Plane mirror doesn't have any power, so power of mirror is 0 because it's plane mirror. Total power is 2PL plus PM. So 2 into PL was found to be equal to 1 by 4R plus PM is 0. So this gives you 1 by 2R as the power of the device. Now if power is P, certainly focal length is given by the reciprocal of that. So the focal length F of the device is equal to 2R. So this is the equation for the focal length of the device. Now they say that this focal length is equal to 0.2 meter. The argument is that the focal length of the device is equal to 0.2 meter. So the focal length is actually 2R and that is given to be equal to 0.2 meter. Now they ask you what is R. Answer is 0.2 by 2, which is equal to 0.1 meter. So the radius of curvature of the lens is given to be 0.1 meter. Option is 4. That was 12. Okay, question number 13. A plano convex lens having radius of curvature of first surface 2 cm exhibits a focal length of f1 in air. Another plano convex lens with the radius of curvature 3 cm has a focal length of f2 in a liquid of a refractive index 1.2. Now both lenses are made of same glass of refractive index 1.5. Then what's the ratio f1 by f2? So these are two lenses. One lens is having radius of curvature 2 cm, other is 3. And first lens is in air, second lens is in liquid. Okay, so let's go to the experiment here. 2 cm is the radius of the first lens and that is in air. Okay, so could be this. I have given you a diagram here. This is the radius of curvature 2 cm and the refractive index inside the lens is 1.5 and the medium is air, surrounding medium is air for the first lens. Now the focal length of that lens is supposed to be f1. I think you have a direct equation for this. I hope you remember that. If a plano convex lens is placed in air, then I will advise you to remember this expression. The focal length is directly given by r by mu minus 1 or n minus 1. So in that way, the radius is 2 centimeter. So divided by mu minus 1 is 1.5 minus 1. So that's a direct equation for the focal length of any plano convex lens in air. So 2 by 0.5 is 4 centimeters. So we directly get the focal length of that lens because it is used in air. Now coming to second lens, they say that second lens has a radius of curvature 3 centimeter and the refractive index continues to be the same as 1.5. But the issue is that the surrounding medium is not air anymore. The n here is equal to 1.2. So that is a lens immersed in liquid. So we have to apply the lens maker's formula to find the focal length of that lens. 1 by f equal to n2 minus n1 is 1.5 minus 1.2 divided by again 1.2, that into 1 by r1 minus 1 by r2. I can say 1 by infinity minus 1 by minus of 3 because the second radius is negative. Okay, simplifying this, I have 0.3 divided by 1.2, that into some 1 by 3. Yes, that is 1 by f. So this gives you the focal length f as how much? Okay, 3 cancel, you'll get 12 centimeter. That is f2. So this is f1, this is f2. So f1 is 4, f2 is 2. They ask you what is the ratio of focal lengths, f1 by f2. It is 4 by 12. It is equal to 1:3. So the ratio is 1:3. Your option is 2. That was 13. Moving on to 14. A photograph of a landscape is captured by a drone camera at a height of 18 km. The size of the camera film is 2 cm into 2 cm and the area of the landscape photographed is 400 km squared. Then the focal length of the lens in the drone camera is. See, this is an object which is which is far away from the lens here because it's a drone camera flying 18 km high. So when compared to the focal length of that lens, the distance to the object, so-called landscape, is much higher than the focal length. So it's a far object and the lens will produce a real image also. Forget about the landscape and all. I'll just give you one case where an object, not a landscape, let's say some tall object is there and this object is OB and this is a convex lens, the image formed on the other side is IM. Okay, it is not a full ray diagram, but at least I have shown a light ray passing through the optic center of the lens. Whatever be the distances to object and image, make sure of one thing, these two angles will be always equal. So the angle subtended by the object and image at the optic center of any lens, that they'll be equal. So these two angles are equal. So as these two angles are equal, I can say the two triangles you can see in the figure are similar triangles. If you say, for example, this is U and this is V, then certainly the triangles are similar. For example, if you take here OB divided by U, because this OB, this by U, will be equal to this IM divided by V. So that logic is applicable here. Now, when you have an object far away, I can say in this case, the object is very far away. It is said to be 18 km and all. So this is an object that is far away. This distance is 18 km in our question, which means this V will be very close to F. The image will be almost formed at focus of a lens if the object is far away. So the V is equal to F here. So this is the idea we are going to use. Now let's see what the question is all about. The question is about a lens forming an image of a landscape. Let me show it in this way. You can consider this to be the landscape. Now this is the drone camera and this is the image produced. They say that this landscape is having an area of 400 kilometers squared. Now the image is only very tiny. Image is very tiny because they say that the screen or film that is used to capture this image is only having 2 cm into 2 cm area. I think it is 2 cm means it is 4 centimeters squared. Then what is the focal length of the lens is the question. I think they are asking what is focal length, isn't it? Yeah, focal length. So let me do one thing. This is the real, okay, almost real picture. I'll make it much more simple for you. I'll just take this object a little further above so that it looks like this. So this is the landscape and this is the image. Now I told you that these two angles are always equal. Now coming to sizes, it is said that 400 kilometers squared is the size of the landscape. I can say it is 20 kilometer into 20 kilometer. That is how the area of the landscape is 400 kilometers squared. So let's say 20 kilometer, 20 kilometer. So the vertical height, you know, this is 20 kilometer. This one is 20 kilometer. Okay. Now this coming to image now, it is 2 cm into 2 cm. I'm coming to this part, this image. That image is having a size of 2 cm into 2 cm. So this is also 2 cm. Now I told you that this V is equal to F here. We'll find what is the value of F now. Okay, these two triangles are similar. And one more thing, this distance is 18 kilometer. They say that the object is at a distance of 18 kilometer because the drone camera is flying 18 kilometer above ground. So the distance is 18 kilometer. All right. Now let's take side by side. 20 kilometer by 18 will be equal to, yes, 2 by F. Taking the law of similar triangles. Okay, let me write 20 kilometer divided by 18 kilometer is equal to, on the other side, I have 2 centimeter divided by F. Okay. Now the question is, what is F? It is going to be, F is equal to 2 into 18, yes, 36 divided by 20 in centimeters. You are getting 1.8 centimeter. That is the focal length of the lens. 1.8 centimeter, option A. That was 14. Let me go to the next question, which is about a thin prism. A thin prism P1 with an angle of 4 degrees made of glass with a refractive index of 1.54. It is combined with another prism P2 made of glass having a refractive index of 1.72 to get dispersion without deviation. So there is no deviation. Forget about dispersion here. They say that there is no deviation. The two lenses coupled together will produce a net deviation of 0. Simple as that. Angle of prism P2 in degrees is. So this question is about deviation, not dispersion. Remember, when you pass light through a small angle prism, light will have actually a small deviation. If the angle of prism is not much larger, you can expect only a small deviation. If this is the actual path of light ray, light will take a small bend like this. Now that deviation d, you must remember, it is given to be equal to n minus 1 into a, where n is the refractive index of the prism. It is supposed that the surrounding medium is air in this expression, then a is nothing but the angle of prism. So the deviation is given by n minus 1 into a. And always remember, the deviation will be towards the base of prism. I have shown here this as the base of the prism. Actual path of light ray was this. Look at the way the light ray is turning. It is turning towards the base. So that approximate equation deviation is given by n minus 1 into a. Now, the question is, what is the angle of the second prism in such a way that the total deviation is 0? So when you have two prisms kept in inverted ways, you have first prism, you keep the second prism in inverted way like this, then of course deviation produced by the first prism can be cancelled using the second prism. So what should be the angle of that prism so that it happens? So here we must assume that light is passing through the prism. First of all, it makes a deviation like this. Now the second prism will produce another deviation like this. So the total deviation, let's assume that D1 is a deviation produced by the first prism and D2 is a deviation produced by second prism. Then the demand of the question is this: d1 by d2 must be equal to 0. So what should be the angle of second prism? That's it. So d1 and d2. Remember, d1, if it is the deviation produced by the first prism, I'll say the first prism is actually making a deviation this way. So this is d1. Now the second prism will produce actually a deviation in this way. It is d2. This is d2. And these d1 and d2 are opposite. So if we have d1 as positive, certainly d2 is going to be negative. So d1 plus d2 is equal to 0 becomes d1 plus minus d2 equal to 0. So I'm putting a minus sign here, which means that d1 must be equal to d2. So the deviation produced by the two prisms must be numerically equal. Then only they will completely cancel out to give you 0 deviation. Now let's put values. d1 is n1 minus 1 into a1 is equal to d2 is n2 minus 1 that into a2. Now let me put values. n1 is given to be 1.54. Okay, this is 1.54 minus 1 that into a1 is given to be 4 degree. Okay, I'm not changing units here. I'll get the answer also in degrees. n2 is given to be 1.72 minus 1 that into a2. That's our calculation. So it is going to be 0.54 into 4 degree is equal to a2 that into 0.72. You got a2 here. It is 0.54 that into 4 divided by 0.72. Simple now. 0.54, 54 by 72. It is 3 by 4. Yes, you will get the, sorry, it is angle. So it is 3. You will get a2 as 3. Now since a1 was used as degrees, in degrees, a2 also will get in degrees. So a2 is equal to 3 degree. That's your answer. So the angle of the second prism is 3 degree. Yes, this is in degrees. It is 3. Let's move on to the next question. A hemispherical vessel is completely filled with a liquid of refractive index mu. A small coin is placed at the lowest point of the vessel as shown in the figure. The minimum value of refractive index of the liquid so that the person can see the coin from the point E is. So here is a hemispherical bowl in which something like water is there, and there is a coin placed inside the bowl at the point called O. There is a coin or some object placed. Now you know the coin is visible from all directions because light will come out. Now the condition here is this. The demand of the question is that this coin must be visible. So the coin is supposed to be here. This coin must be visible for an observer standing here. Actually, here is the observer's eye. So there is an object kept here. Light rays will come out certainly. So this is the way we can expect light rays to come out and all. Now for this guy, this object must be visible. So for that, the refracted ray must somehow reach his eye. Now let's take a diagram and understand it perfectly. Here is the object. Let me assume that this is the so-called coin in the question. That's at point O. Now, when you consider light rays going out, you know, let's say if this is a light ray, it's a normal ray that goes out without any bending. So that's the way we can expect light rays to go out. Now here, you can expect a lot of light rays. If you take an oblique ray like this can pass like this also can pass like this. Now finally, there is an observer standing here. His eyes are here. So that's the location of the observer. So I'm just showing the position of the observer's eye. Now for this guy to see this coin, a refracted ray must at least one refracted ray must reach his eye. Now it can be this. For example, this light ray can bend like this. It may take a bend to refract like this. Of course, the observer will be able to see that. But that requires a lot of refractive index because, you know, a light ray passing like this and bending in this way requires a lot of refractive index because that's a huge refraction. They ask you what is a minimum refractive index. So when it comes to minimum refractive index, we'll consider this light ray. At least this light ray, if that is able to bend in this way, the observer will be able to see the object. So I'm considering that ray. So let's say this is that ray. That's a ray falling at this edge. Now after refraction, if something like this will happen, see, the observer will be able to see this object. Now the question is, what is the refractive index required for this to happen? Now let's come to refraction. Laws of refraction we can apply. If you have a normal here, certainly this angle will be angle of incidence. And of course, that is clear here because the radius of the hemispherical bowl, if it is taken as r, then certainly the other is also r. R is the radius of curvature, and this is an isosceles triangle making this angle conveniently 45 degree. If that is 45 degree, this is also, remaining angle is also 45 degree. Now the angle of incidence for that ray, this is an incident ray, it is 45 degree. Angle of refraction, as you see in the figure, is 90 degree. Now the question is, what is the refractive index required? So if you suppose that n is a refractive index, we can apply law of refraction here. It's going to be easy now. N into sine 45 degree, that is equal to 1 into sine 90 is the condition that this coin or so-called object is visible for the observer. Okay, n into sine 45 is okay, n divided by root 2, that's equal to 1 into sine 90 is 1. Yes, this makes n root 2. So the minimum refractive index for the observer to see this object is root 2. Actually, for any refractive index larger than root 2, the guy will be able to see that. But here, it's about the minimum refractive index. So it is going to be root 2. So which is that? Yes, option is 4. Let's go to the next one. A concave mirror produces an image of an object such that the distance between object and image is 20 centimeter. It's a concave mirror. It's a real image because the magnification of the image is said to be -3. Then the magnitude of radius of curvature of the mirror is. So there is an object placed in front of a concave mirror. The image is real, that's very clear from the statement here, because the magnification is -3. A negative sign of magnification indicates that the image is real. So altogether, it may look like this. You can assume that this is the object. Let me say that is OB, and this is the image. This is supposed to be the real image. Now, since they have said that the magnification of the image is 3, the image is magnified 3 times, this makes it clear that if this distance is u, let's say this distance is u, and I'm supposing that that is x, for example, it is taken as x, then the distance v must be 3 times that, because magnification is also v by u. So if 3 is the magnification, certainly the v must be equal to 3 times the value of u. So if you take u as x, it's clear that the value for v is 3x, because the image is 3 times magnified. They clearly say that linear magnification is -3. Okay, so that's a hint we have. Now the second hint, direct hint given in the question is that the distance between image and the object is 20 centimeter. That gives us a value for at least x now. So this gap, for example, this one, that is given to be exactly 20 centimeter. That's clearly mentioned in the question. Now, the question is, what is the radius of curvature? Let's try to find what is focal length using distance formula. But before that, you have actually scope of finding what is x here, because in this case, this gap is going to be, this gap, 20 centimeter, that is going to be this 3x minus x. So 3x minus x is 20. Let me begin with that. 3x minus x is equal to 20. This makes 2x 20. Therefore, the value of x is obtained as 10 centimeter. So value of x is 10, that means u is equal to 10. Therefore, v is equal to 30 cm. So we have both u as well as v. Now the question is, what is the radius of curvature? Let's find what is the focal length using distance formula first. So distance formula for any mirror is 1 by v plus 1 by u is equal to 1 by f for any mirror. Now putting values, 1 by v is minus of 30 plus 1 by u is minus of 10 is equal to 1 by f, where f is unknown. Let's simplify this. This 30 plus 10, 40. So this is 40 divided by 300. That's minus of, that is equal to 1 by f. This gives the value for f as 30 by 4, minus of 30 by 4 in fact. Or I can say it is 7.5 centimeter. That is the focal length. Focal length of the spherical mirror is 7.5 cm. Now they ask you what is the radius of curvature. Now radius of curvature for any spherical mirror is 2ef. So that is 2 into 7.5. In fact, it is 15 centimeter. Now the negative sign, of course, I have discarded, because the negative sign only shows that the mirror is concave. Now they ask you what's the magnitude of radius of curvature. So the magnitude of radius of curvature is 15 cm. It's a concave mirror with 15 centimeter radius of curvature. Here is the next question. A long glass tube mixture of two liquids A and B with refractive indices 1.3 and 1.4 respectively forms a concave refractive meniscus towards A. So that's a spherical meniscus. If an object is placed at 13 centimeter from the vertex of the meniscus in medium A, it forms an image with a magnification of -2, then what is the radius of curvature of the meniscus? So this is about refraction taking place at spherical surface. But this is not only about distance, it's also about the size of image. So you must have two concepts at least at your hand. One is a distance formula that tells you the relation between distances u, v and r. Secondly, it's about magnification as well. Okay, let me just show what is explained in the question. They say that some point source, possibly it's a point source. No, it's not a point source. It looks like an extended source because the question is also about magnification. So let me just assume that there is an object kept here. Okay, this is the object O inside medium. This can be considered to be a long tube, maybe a glass tube. There are two liquids with refractive indices n is equal to 1.3 here and n is equal to 1.4 here. So these are two immiscible liquids and there is a convex meniscus here. You can see some spherical surface here. Now what is the radius of curvature of that spherical surface is the question. Now when you have an object here, certainly a corresponding image will be formed on the other side. Let me assume that this is image. Now the hint they are giving you is that the magnification of this image is m is equal to -2. So this is given m equal to -2. Let's now see what's the relation between distances. If you consider this distance as u, the object distance is supposed to be u then, okay. This is supposed to be u and this distance is what we call actually v also. I hope it is visible on your screen. This is u and this is v. Now let's apply the distance formula here. You know that for any refractive, any spherical refracting surface, n2 by v minus n1 divided by u is equal to n2 minus n1 divided by r. That is the equation for connecting the distances in spherical surface. Now let's put values. Of course, n2 is 1.4 here because that's the second medium. Divided by v is at least unknown here. We don't have any idea about what's v now. Yes, minus n1 is okay, 1.3 divided by u is there because it is said that this u is equal to 13 centimeter in the question. That's a given input. Now that 13 is measured backward, so it has to be -13 here. This is equal to n2 minus n1, okay, it is 1.4 minus 1.3 divided by the unknown radius of curvature. So in this equation itself, there are two unknowns. So we require one more equation to deal with this, and that is why they had given us the magnification of the image. But this is magnification of image produced by a spherical surface, spherical refracting surface. So we have to prepare some equation for magnification here. So let me try to find an expression for magnification using this diagram. Just assume that there is an object like OB as we mentioned earlier. This is the image and I consider the distances as u here and this distance is supposed to be v, the distance to object and image. Now I have shown some light ray, some random ray. Okay, there are many light rays passing through the spherical surface. That is how the image is produced. But I have shown only one ray here. That ray is the ray falling on the pole of the mirror, sorry, spherical surface. And then, okay, this is the way it passes. It undergoes refraction. Let's assume that this angle is, for example, some θ1 and this angle is θ2. Now, linear magnification is nothing but the ratio of height of object and height of image. So let me assume that this is HO and this is height of image HI. Linear magnification basically is HI divided by HO. That's it. Now to find what is HI by HO, I think we will apply law of refraction here. For example, we consider this as N1 and this medium to have a refractive index N2. Now this light ray undergoes refraction. So N1 into sine θ1 must be equal to N2 into sine θ2, which is law of refraction. That is what I am writing here. N1 sine θ1, that is equal to N2 sine θ2. This is nothing but law of refraction. But my dear friends, the angle I have shown here is not a large angle. Please assume that these angles are not much large. They are small angles. If angles are small, then we are free to make a compromise here because sine theta is approximately equal to theta when theta is very small. That is what we do here. Assuming the theta is not much large, let's say sine theta is equal to just theta. Sine θ1 is just θ1 and the term sine θ2 becomes just θ2. So let me rewrite this as n1 theta 1 is equal to n2 into theta 2. For small angles, that relation is also almost all right. Now let's bring distances. Okay, theta 1 is this angle. I can use angle equal to arc by radius concept. This is angle, this is arc, and this is the radius. So theta 1 angle is equal to arc by radius. That's what I use. So this theta 1 can be written as HO, N1 into HO divided by U. Now this is equal to, it is N2 into theta 2. This is N2. Theta 2 is given to be, yes, this is theta 2 equal to arc by this radius. Angle is arc by radius. So theta 2 is HI divided by some V. Let's simplify this to get what is HI by HO, because this HI by HO is linear magnification. So HI divided by HO, which is going to be later known as magnification, this is going to be equal to N1 divided by N2, that into V divided by U. So this is the equation for HI by HO. Now, before we come to a final equation, we must put sign conventions to make it a standard equation, because if you're going to use this equation in all cases, then it must be suitable for all cases. So the rule is to apply. So the way what we do here is we apply a sign convention there. So according to sign convention, new Cartesian sign convention, look at this. This HI is taken as a downward measurement. So that HI will be given a negative sign. Look at this HO, that's a positive measurement, so that HO is positive. N1, N2 are refractive indexes, they don't have signs, but V and U are distances. Look at this, V is a measurement that is taken forward, therefore it will be considered as positive here, okay. V is positive. Then U, look at it, this is U, this distance is U in fact, so that U is measured in the opposite way of incident ray, that must be considered as negative also. That's how we use a sign convention. Now let's simplify this, because there are plus, minus and all. Now if you eliminate everything, finally you'll see that the effective result is that HI by HO is equal to, finally again back to N1 by N2 into V divided by U. Now this HI by HO will be known as magnification. So my dear friends, when it's a refracting spherical surface, you can remember expression for magnification as this, N1 by N2 into V divided by U. That can be used as an expression for linear magnification whenever the surface is spherical like this. Okay, now let's make use of this result. This result can be used to find out at least what is V here, because in the question it is said that the linear magnification is minus of 2. U is also given. N1, N2 are also there. So you can directly find what is at least V here, because M is given to be minus of 2. N1 is okay, 1.3, because in the question N is given to be 1.3, and N2 is equal to 1.4 also. So 1.3 divided by 1.4, that into. Now comes V by U. V is only quantity that is unknown here, and U here is 13, but that is minus of 13. You remember, this U was given to be 13 cm in the question. So that is minus 13 according to sign. So this tells you the value for at least what is V. So let's see what is V. 1.3, 1.3, 20. Yes, it is going to be 28 centimeter, isn't it? Correct? Because 13 and 1.3, 10 times it is 28. So the V, the distance V, we got as 28. All right. So this is what we got. It is 28 centimeter. Now it's a matter of calculating a radius of curvature. Yes, because this V is what we got as 28 centimeter, and that 28 is positive. So let me replace that V with 28 now. So we have this as 28. Okay, 1.4 divided by 28 is going to be 1 by 20. I think this is 1 by 20 plus it is 1 by 10 is equal to 1.4 minus 1.3 is 0.1 divided by radius of curvature. Yes, that is going to be, now let's see, 10 plus 20 is 30 divided by 200. Yes, this is equal to 0.1 divided by radius. This gives you radius R as a, yes, it is 20 by 3 into 0.1. That will be some 2 by 3 centimeter. So finally, the radius of curvature of this surface is 2 by 3 centimeter. Let's see what that is. Yeah, option is 4. Moving on to the next question. Let U and V be the distances of object and the image from a lens of focal length f. The correct graphical representation of U and V for a convex lens will be. So this is a UV graph. Actually, we are familiar with UV graph. Even without explaining it, you must be able to identify which graph is that. But anyway, I'm just explaining how you got that graph by taking a few points in the graph. It's a convex lens. It produces a real image. Okay, it is said to be this U is greater than F. See, this U, if it is greater than F, certainly the lens will be forming a real image. So I'll just give you some important points just which helps you to plot the graph here. If you place the object at a very, very large distance from the lens, for example, you are keeping object at infinity, far away from the lens, then a real image is formed almost at the focus. So I can say the position or distance the image will be almost equal to focus. The image will be almost formed at the principal focus of the lens. So when U equal to infinity, V equal to F. Actually, when U equal to infinity, V equal to plus F. Now there is another important point for a convex lens. When you place an object exactly at 2f, then image also is produced at 2f. So when you have U equal to minus of 2f, certainly V will be equal to 2f. So that's another point in the graph. So these points can be used to plot the graph very easily. Okay, now finally, if you're keeping the object exactly at focus, at U equal to minus of f, then you'll find that V is equal to infinity also. If we keep the object at focus, then the image will be formed far away from the lens. So these are three important points I can just use to determine the nature of graph here. Of course, the graph is this because when U is equal to infinity, this one, see this point, when U is equal to infinity, the point is here. Now, when U is equal to minus of 2f, okay, this is the point I meant. When U is equal to minus of 2f, V is equal to f. If this is 2f, this is also 2f, like this. So this is the graph anyway, UV graph. So this must be remembered. In fact, you must have actually drawn this graph in your lab while doing experiments on lenses. Okay, that's a familiar graph. Let's go to the next one. Two light beams fall on a transparent material block at points 1 and 2 at angles theta 1 and theta 2, as shown in the figure. After refraction, the beams intersect at a point 3, which is exactly on the interface at the other end of the block. Given that the distance between 1 and 2 is 4 root 3, that's hint number 1, then theta 1 and theta 2 are equal. Even though they show two angles here, you are free to assume that they are equal. Theta 1 or theta 2 both are equal to some theta. Okay, that's an unknown angle, but still a hint is given. Theta 1 or theta 2, they are equal to cos inverse of n2 by 2n1. That's another hint. Now here, you are required to find the refractive index, where refractive index of the block n2 is greater than refractive index of outside medium. Then you are required to find the thickness of the slab. So how thick is a slab is it? Okay, so what they mean is this: if this is the light ray, these are the two light rays, you know that after refraction, this is the way they bend. Now, after bending, they are supposed to meet at this point exactly at this point called 3. If that exactly happens, then what could be the thickness of the slab? Okay, let's go to the side of calculation. I have a better figure for you. So these are the two light rays. These light rays will take a bend. They'll bend towards the normal. They're going to hit here. This point is actually called 3 in our diagram. Okay, thickness of the slab. Okay, I'll just begin with that. That is going to be T. Now this T is to be determined. Now, let's also mention that this distance, which is this distance, this one, that is given to be 4 root 3 here. We'll use it later. 4 root 3 centimeters that. Let's apply law of refraction at least here. This is the normal. I can say this angle is some I and this is some R. Then n1 sin A equal to n2 sin R is applicable. It is given that this angle is theta 1 and this angle is theta 2. These are the angles given, but don't worry, they are equal. I can say both are equal to theta. Theta 1 or theta 2 both are equal to theta. Now let's apply law of refraction here. Let's suppose that n1 is a refractive index here and this is n2. They are using n1 and n2 in the same way. Let's apply law of refraction now. n1 into sin I, that is angle of incidence, is equal to n2 into sin R. That is law of refraction. Now this I, this angle I is of course 90 minus theta. Because this angle is theta means of course this is going to be 90 minus theta. So for I can use 90 minus theta. Let me rewrite the equation as n1 into sin 90 minus theta. that is equal to n2 into sine r. It is the same law of refraction rewritten. Okay, now let's see what is sine 90 minus theta. Sine 90 minus theta is cos theta. So n1 into cos theta, that is equal to n2 into sine r. This is actually law of refraction. Now let's go back to the question and see some other hint given. Let's make use of that hint. This is mentioned. Theta 1 equal to theta 2, which is equal to theta. What they are trying to say is that the so-called theta here is equal to cos inverse of n2 divided by 2n1. That's the statement given. Now here, if theta is equal to cos inverse of this, certainly cos theta will be equal to n2 divided by 2n1. Okay, it's a hint they had given. So this cos theta is n2 by 2n1. So here I have a cos theta here, this one. This can be written as 2 into, sorry, what is that? n2 by 2n1. So this is n2 by 2n1. And yes, there is n1 also equal to n2 into sine r. Let's simplify this. You'll see that this n2, n2 cancel, n1, n1 cancel to give you sine r 1 by 2. So that's a very convenient angle. Sine r is equal to 1 by 2 indicates that r is equal to 30 degree. So we got at least this angle. This angle is obtained as 30 degree. Now it's easy. You're required to find what is this t. See, if this angle is 30 degree, this is also 30 degree being opposite angle. Now this distance, I come to this distance alone, this one. It is given that this total distance is 4 root 3 centimeter. That is given in the question. If it is 4 root 3, certainly this distance, I mean this one, that is going to be half that distance. So certainly that will be 2 root 3. 4 root 3 by 2, that is 2 root 3 centimeter. That's the distance. Now finding t is easy. Now we'll apply simple trigonometry. This angle, opposite, adjacent, tan is better. I'll take tan theta and finish this. Tan 30 degree is equal to opposite 2 root 3 divided by t. Now tan 30 is 1 by root 3. 1 by root 3 is equal to 2 root 3 divided by t. Solving this, you'll get t as a 2 into 3 into 3. Yes, it is 6 centimeter. So thickness of the slab is 6 centimeter. Numerical value of the answer is, yes, 6 centimeter. That was it. Two identical symmetric double convex lenses of focal length f are cut into two equal parts L1 and L2 by AB plane and L3 and L4 by XY plane as shown in the figure respectively. The ratio of focal lengths of the lenses L1 and L3 is. So what are these L1 and L3? They clearly show, yes, this is a full convex lens. Now that convex lens has a half here. That half is actually called L1. Now in the second figure, this half, if you cut the lens in a different way, again you'll get two halves. Now this half is known as L3. So the question is, what is the ratio of the focal lengths of these two parts? Okay, I have a better figure for you. Here is it. This is a lens which has a focal length of f, for example. If that is f, they mean L1 as this. This is the L1. Okay, see, this is the L1. That is L1. So the focal length of that is to be determined. You know that when a lens is cut in this way, if a lens is cut in this way into two pieces like this, nothing will happen to focal length at all. The focal length remains unchanged, so therefore the focal length of this will continue to be f. But if you cut the lens in this way, if this is the way you're cutting it, then the focal length is doubled. Then this f will become 2f, you know. It becomes two planar convex lenses, and a single planar convex lens has actually twice the focal length of an equiconvex lens. So in that way, this focal length is 2f. It's simple. Now they ask you what's the ratio of focal lengths of L1 is to L3, isn't it? Yes, L1 is to L3 means this f divided by 2f. So L1 is to L3 is f is to 2f, which is equal to 1 is to 2. So the ratio is 1 is to 2. Yes, your option is 2. Okay, moving on to the next question. A convex lens made of glass with refractive index 1.5 has a focal length of 24 centimeter in air. When the same lens is totally immersed in water with refractive index of 1.33, then the focal length changes to what value? So lens has a certain focal length in air. You know well that when the lens is immersed in liquid, it behaves as a different lens with a different focal length, because when surrounding medium changes, you know, certainly the performance of the lens also will change. Okay, what is said here is this. The refractive index of this lens, is given to be n equal to 1.5. Radius of curvature is not known to us. It's only said that it's a convex lens. Maybe it's a biconvex lens. So at least the radii are unknown. We don't require it also, because when you write two equations and divide, they're likely to cancel out. Now, given that the focal length of this lens, when used in air, is 24 centimeters. So n equal to 1 at least in the first case. Now, the same lens is later. Same lens means the refractive index continues to be 1.5 inside. But the same lens with radius of curvature R1 and R2 now is immersed in liquid. Now, that liquid is having a refractive index how much? It is 1.33. 1.33, of course, in fraction it is 4 by 3. Okay, this can be written as 4 by 3. I'll make it 4 by 3 for convenience of calculation. So n equal to 4 by 3, that's the refractive index of the surrounding medium. Now the question is, what is the focal length f2 of this lens in this medium? So it's just an application of lens maker's formula, because that equation tells you the relation between focal length, radius of curvature, refractive index and all. And you know that focal length of any lens in any medium is given by this expression, n2 minus n1 divided by n1, that into 1 by r1 minus 1 by r2. That's a full lens maker's formula. We are planning to apply this formula in two cases. Let's see what we get here. It is 24. So let me put values. 1 by 24 is equal to, n2 always stands for lens, n1 surrounding. So I have it as 1.5 minus 1 divided by 1, that into 1 by r1 minus 1 by r2. I'm not giving any value for r1 and r2 because later that term is going to be cancelled. Okay, 1 by 24 is equal to, it is 1.5 minus 1 is okay, 0.5. 0.5 can be written as 1 by 2. Okay, that into 1 by r1 minus 1 by r2. Let me keep it as equation number 1. That's for first lens. Let's repeat the same thing for second lens now. Second lens is having an unknown focal length. Let me write 1 by f2 is equal to n2 minus n1. I'll take here 1.5 as 3 by 2. Okay, so this is 1.5, which can be written as 3 by 2. So 3 by 2 minus 4 by 3 divided by again 4 by 3, that into 1 by r1 minus 1 by r2. That is lens maker's formula for second lens. Okay, it is 1 by f2 is equal to 3 by 2 minus 4 by 3. What is that? 9 minus 8 by 6. It is 1 by 6. So it is 1 by 6 divided by 4 by 3. Ooh, okay, that into this. So this 1 by 6 by 4 by 3 is 1 by 24, isn't it? No, 1 by 24, no. It is 3 by 24. 3 by 24 gives you 1 by 8. Okay, so simplifying this, I'll get 1 by 8. This is 1 by 8 into 1 by r1 minus 1 by r2. That is my expression 2. Now it's a matter of just comparing these two equations. We'll divide them. So when you divide left-hand sides, I'll get f2 divided by 24. f2 by 24 on the left side is equal to what? Yes, it is 4, because 1 by 8 by 1 by 2 is 4. f2 is equal to 4 into 24, which is 96 centimeter. So the focal length of the same lens in liquid is 96 centimeter. That is option 2. Here is the last question. Two concave refracting surfaces of equal radius of curvature and refractive index 1.5 face each other in air as shown in the figure. A point object O is placed midway between P and B. The separation between the images of O formed by each refracting surface is. Let's study the experiment very carefully. Here is one spherical surface, identical spherical surfaces here. Both are made of glass and the refractive index of both the surfaces are 1.5 each. Now the gap between these two surfaces, from this to this gap is given to be 2r. Radius r plus r, that is 2r. Now there is an object placed midway between them, in between them. It is not exactly at midpoint. They say that object is here. That's the figure. Now this distance is r by 2, while this is given to be 3r by 2. So 3r by 2 plus r by 2 is okay, equal to 2r. That's the way the object is placed. Now the question is, what is the separation between the two images formed by the two surfaces? You see, when there is an object here, light will be passing in this way through that surface. Maybe this is the way light refracts, As a result, there will be some image. Is that real image here or virtual image here? No idea. We'll have to find out. Similarly, this object O is spreading light in this way as well. So this surface also will actually produce an image of this object, maybe real or virtual. So that's the second image. So we have to find the location of two images here. One is I1 and the other is I2. So let's do one thing. Let's actually do this separately. Actually, the question has, I have a neat figure here. This is the object. Okay, this one is the object. Let's first of all find what happens when light is passing in this way to that surface. I'll come to that image first. I'll be calling it I1. So let me do one thing. This surface alone is shown in this figure. Okay, for convenience, I have erased the other figure for the moment. So this is the object. Now, given that this distance is r by 2, the distance u, you know, that's given to be r by 2. Refractive index of this medium is 1.5. And here it is supposed to be air, so it is 1. Let's apply r as a radius of curvature also. Let's apply distance formula for spherical surface. Hope you have not forgotten that. N2 by V minus N1 divided by U is equal to N2 minus N1 divided by R. That is the distance formula for any spherical surface. Okay, let's put values carefully. Remember, this is the object, light is passing in this way. We have to use the values of distances according to that sign. Okay, N2 is a second medium, which is 1.5 by your V here. That V, distance V is unknown for us, that is to be determined, minus N1 is 1 by U. The distance to object is r by 2. Look at this, this is the distance U, but that is measured backward. Therefore, it has to be minus r by 2 equal to N2 minus N1, 1.5 minus 1 divided by radius of curvature r. See here, this r is minus because you have actually an r here. This is the radius of curvature. So center can be somewhere here. The measurement of radius of curvature will go this way, which is opposite to incident light. At least for this surface, you know, light is passing in this way. So the radius has to be minus. That's it. Okay, now let me simplify this. 1.5 divided by V plus 2 divided by R is equal to, on the other side we have 1.5 minus 1 is 0.5 divided by R, it becomes 1 by 2R, and that is also minus. Yes, for the simplification will give you this, 1.5 by V is equal to, it is minus of 1 by 2R minus 2 divided by R. So it is 2 plus 1 by 2 is 5 by 2. This is going to be 5 by 2R, which is minus 1.5 divided by V is that. Therefore, V is equal to 2R into 3 is going to be 3 divided by 5. That much times minus 3R, 3 by 5R. So minus 3 by 5R indicates that the image is virtual because you have kept the object here. So image has to be somewhere here, which is a virtual image. So what must have happened is this, maybe this is the way light rays were passing, and after refraction, this is the way they go. Now for an observer sitting here, the image may be seen here. So this is the virtual image. That is the position of the first image. So in my figure, it can be somewhere here. I suppose this is the position I1. So what we got is this distance now. This distance is obtained as 3 by 5R. Okay, let me go back to the original figure and show it. If this is the object, I'll show the position of image. This is the image. Let me call it I1. What I got is this distance now. Now that distance is obtained as this one. This is obtained as 3 divided by 5 times R. That's the position of the first image. In a similar way, we find the position of second image. Now you see light will pass in this way. Because of that, refraction can take place. So this can be somewhere here. There is a second image expected here. We'll find it. Let me go to my next figure and show that. This is the object. This distance is given to be 3 by 2R in the question, because this object is at a distance of 3 by 2R from the other surface. Now radius of curvature is R. N is equal to 1.5 here. Here it is N is equal to 1. Now see, light is coming in this way. This is the way light is passing. This is the way it can bend also. So this is the direction of light. So any measurement towards left is positive here. Any measurement towards right will be negative. Okay, because light ray is passing from right to left here. Okay, applying the equation again, N2 by V. N2 by V. See, this is the way light ray is passing out. Okay, this is the way. That is the way light ray goes. So N2 is 1.5 again, which is second medium, by V is again unknown, minus U is 3 by 2R. So N1 is 1, divided by N1 by U. U is 3 by 2R, but that again is minus of 3 by 2. Is equal to N2 minus N1 again, 1.5 minus 1 divided by R. Radius again is minus R, because this case, center can be somewhere here. Radius will be measured for that surface like this, which is opposite to incident light. So this is minus. So I have a minus sign here. Okay, let's simplify. 1.5 by V minus becomes plus 2 by 3R is equal to minus of 1 by 2R as we got earlier. This gives us 1.5 V is equal to minus of 1 by 2R plus minus of 2 by 3 times R. So it is 1 by 2 plus 2 by 3. What is that? 1 by 2 plus 2 by 3. It is 3 plus 4, 7 by 6. Okay. So this is equal to minus of 7 by 6 R. That is 1.5 divided by V. Therefore, V is equal to 6 into 1.5 is 9. So 9 by 7 times R, which is minus. Okay, 9 by 7 R. Let's see, 9 by 7 R. Where can be this? It can be somewhere here. If this is the object, maybe somewhere here is that this is the position of image. This distance is what we got as 9 by 7 times R. So this is 9 by 7. Let me go to the original figure and show that. See, for this object, if this is the object, the second image is supposed to be somewhere here, I think. Okay, so I'm just taking that image to be here. Possibly it will be here, I suppose. So this can be I2, like this. Now, if that is I2, then the distance, this one is obtained as, what is that? 9 by 7 times R. So this distance is that. Okay. Now, finally, the question is, what is the gap between these two? What is the distance between the images I1 and I2 is the final question. So let's say this is X. Then find what is X. Okay, I'm just calling that gap to be X. Then what is X is the question. Let me come to the final step. See, this distance plus X will give you the total distance to R. That's my final step. So 9 by 7 times R plus 3 by 5 times R plus X is equal to 2R. Okay. Let me do that very carefully. 9 by 7, okay, it is 45 plus some 21, which is going to be 66 by 35. Okay, 66 divided by 35 times R plus X is equal to 2R. Okay, X is equal to 2 minus 66 divided by 35 times R. Okay, this is equal to, let me come to final step. 35 to 70 minus 66 is 4 divided by 35 times R. That is X. So X is equal to 4 by 35. Now it is calculation. Okay, you must confirm this. It is going to be 0.1 something like that. Let me go to the option and see what exactly is that. Let me finally write the answer here. The distance X is equal to 4 divided by 35 times R. That is the answer. Now this 4 by 35, when you calculate, you will see that it is 0.114 R. So the gap between these two images in this experiment is 0.114 times R. That was the last question. So my friends, thank you for watching. We'll meet again. Take care. Bye.